In today's video, we're going to be talking about Arduino circuit design and sketch programming. The key topics will be the difference between sensors and actuators, processor boards, Arduino itself, and we're going to do some Arduino sketch examples with some hands-on at the end. So make sure you stay tuned to the end of the video to see it in practice. But we'll start with the theory for now. So the difference between sensors and actuators. So what is a sensor? The sensors are devices that detect and respond to changes in the environment. There are many different types of sensors, but essentially a sensor is an input device which converts signals from different types of energy, mechanical, light, temperature, sound, etc., into electrical energy. For example, a temperature sensor detects temperature and converts it into electrical energy. Light sensor detects light, converts it into electrical energy, detects humans as well, so maybe the shadows that a human might create. A sound sensor detects sound and converts it into electrical energy. Actuators are devices that can be used to move, manipulate, or control the physical environment. An actuator works in the opposite way to a sensor. So actuators receive an electrical signal and translate that into a physical movement or a physical quantity. The physical output could be produce sound, force, or movement of some kind. We're going to look at analog versus digital signals. So the analog signal can take any number of values. However, a digital signal only has two values, high and low, also called a 0 or 1 state. So as shown in the following image, an analog signal is a continuous wave that changes over a period of time, whereas in the second image, a digital signal is a discrete wave that carries information in binary form. Processor boards. The heart of a processor board is a microcontroller, which is an integrated circuit or tiny computer with processor, memory, and input and output ports. Importantly, a microcontroller is programmable. It does not come programmed to perform any task, and therefore must be programmed using code. A microcontroller is not just a hardware component, there's always the software component in an IoT device or building an IoT application. Moving on to Arduino. Arduino is an open source electronics platform. Keep in mind that the integrated circuits alone cannot be directly used as is. They need a lot of surrounding circuitry to enable them to perform the required function. Arduino comes as a full package. It's open source electronic platform designed around a microcontroller to help new learners use and become familiar with the microcontroller. So this is the Arduino Uno anatomy. This is what it would look like. You have the digital pins. The pin 13 is a LED, the only actuator built into the board. This LED is very useful for debugging. Pin 13 there. Power LEDs is this number 3. Microcontroller number 4 is the heart of the board. Analog pins number 5. Number 6 is the ground and 5-volt pins. You use these to provide 5-volt power and ground to your circuits. Number 7 is the power connector. And you'll see in the example videos very clearly what this looks like. TX and RX LEDs indicate communication between your board and your computer. You'll see this in action as well in the demo. USB port used for powering your board and uploading your codes in number 9. And then we have the 10 is the reset button, which resets the microcontroller. As we discussed previously, a microcontroller is sitting inside the Arduino board that needs to be programmed. This is done via IDE, Integrated Development Environment, which will be connected using a Type B USB cable. The ATmega 328P on the Arduino Uno comes pre-programmed with a bootloader and allows you to upload new code without using an external hardware programmer. Please note that if you're not using an integrated board such as Arduino Uno board, and instead we're planning a plain integrated C circuit, an IC chip, you plan to use that, you would need an external hardware programmer with different circuitry components to enable you to program it. In this way, the Arduino Uno board provides us with a ready platform for programming, as you'll also see in the examples. So what is a breadboard? A breadboard is a solderless device for temporary prototyping with electronics and test circuit designs. A solderless device means that it's already internally connected, so no soldering is required to create connections and make them robust. And this on the right is the breadboard. And this is the Arduino Uno. Finally, let's look at Arduino Sketch, the sketch execution and flow. So an Arduino Sketch is compiled, verified into binary and flashed, upload directly to the hardware. The basic sketch structure is verify and upload process. So the sketch is an Arduino program is modularly referred to as a sketch. Verify and compile, checks your C++ formatting syntax and translates it to low-level binary machine code. And the upload flashes the compiled machine binaries onto the hardware processor over a serial connection. Syntax and control structures. So you use the double slash for quick pin local annotations and the slash with the star sign slash at the end for larger blocks of metadata. If statements, you guide program paths using comparison operators, equal to, not equal to, less than, greater than, equal to, inside chained if, else if logic. Loops, use for loops for sequential index-based repetition and while loops for continuous execution. Always update test variables inside to avoid infinite lockups. Built-in I/O and helpers. So I/O stands for input output. the interface through which a microcontroller reads sensory data and writes physical signals. So input, output pins, pin mode sets pin behaviors, digital write/read manages binary states, 0 volts or 5 volts, while analog read measures incoming voltage, and analog write simulates varying output levels via PWM, 0 to 255. Helpers and timing. Built-in formulas like abs, constrain, power, and square root simplify arithmetic, while delay pauses processing. Prefer non-blocking millis timing with the brackets to keep the CPU active. Processes and libraries. So processes are directives like define, which replaces constants to save memory, and include, which pulls in external APIs, are handled before compiling. Do not end these lines with semicolons. Libraries, reusable drivers loaded via the sketch include library, manage, libraries path, and the ID, simplifying complex hardware protocols like SPI communication. SPI communication stands for Serial Peripheral Interface. It is a synchronous full duplex communication protocol used for short distance data transfer between microcontrollers and peripheral devices. And just as well, if you don't know, API stands for Application Programming Interface. Programming ports and serial COM ports and HW microcontrollers connect via virtual COM communication ports over USB using pin 0 and pin 1 for standard serial transmissions on the Uno. ID setup, establish data rates using serial begin speed, for example, 9600, ensure the active ports is selected under tools port. Operating system diagnostics, if a port isn't showing, query terminal using DMESG, pipe grep TTY for Linux, or this other one for Mac to identify the active path. Now for the fun bit of the video, I'm going to give you 3 hands-on examples. First example will be a serial transmitter of periodic message pipelines. The second one will be a blinking LED, physical circuit and digital output. And the third one will be a color RGB LED multi-channel light control. So just a more complicated version of example 2. And I'll get into that right now. What you're looking at right now is the Arduino IDE, which again stands for Integrated Development Environment. This is the main software workspace where we write our C++ code, compile it into machine binary, and send it straight to our Arduino board. When you open up a brand new file, or sketch as Arduino calls it, you are greeted with this clean editor screen containing 2 main blocks of code already built for you. The first thing I want to touch on is understanding void setup. Think of setup as the initialization phase of your microcontroller. The most important rule to remember about setup is that it only runs once, right when the board turns on or whenever you hit the physical reset button. What should we put inside of void setup? So we use setup to prepare our hardware before the main program begins. For example, setting pin modes, telling Arduino whether a pin should act as an input or output using pin mode, starting serial channels, setting up communication speeds to talk to your computer using serial.begin 9600, for example, and initializing sensors, so waking up connected modules or displays. The next thing is void loop. So think of loop as running continuously forever in an infinite cycle. The moment the last line inside loop finishes executing, the microcontroller immediately jumps back up to the loop, the top of loop rather, and starts all over again until the power is cut. So what should we put inside of void loop? So loop is where the actual brainwork and logic of your project live. In here, you will read inputs, constantly check if a button is pressed or a pole temperature data from a sensor, for example. You'd execute logic, making decisions if statements or calculations, and controlling outputs, you'd turn LEDs on and off, drive motors, or stream data to your screen. The quick summary of that is void setup repairs the stage once, and void loop performs the main show over and over again endlessly. Both functions are required by the compiler, but if you leave one of them empty, they must both exist in your sketch for it to run. Now that we understand the structure, let's start adding some real code. Just quickly, I'm going to touch on some theoretical concepts and math calculations. So before sending data from the Arduino to your computer, it helps to understand how data moves physically across the cable. So baud rate measures communication speed in symbols or bits per second. Setting the speed to 9600 baud means the microcontroller pushes roughly 9600 bits across the serial line every second. The critical requirement is that both the sender, Arduino, and the receiver, the computer serial monitor, must operate at the same baud rate. If the computer listens at, for example, 115,200 baud, while the board itself transmits at 9600 baud, the terminal will display garbled text or random symbols. Now we're going to touch on frame period calculation, T-frame. So to transmit a single standard character like the letter A, serial protocols wrap the 8 data bits with control overhead. So one start bit signals the start of the transmission, 8 data bits holds the ASCII character byte, and one stop bit signals the end of the transmission. So this equals to 10 bits per frame. The transition time for one full character frame is 10 bits divided by 9600 bits per second, which equals to around 1.04 milliseconds per frame. The key takeaway is that each individual character sent across the USB cable takes across approx 1.04 milliseconds to physically travel across the hardware lines. We're also going to touch on virtual COM port and USB bridge. So the main processor on the Arduino Uno, ATmega328P, is what it's called, communicates using raw TTL voltage pulses, 0 volts for logic, low, and 5 volts for logic, which is known as high, and on pin 0 RX and pin 1 TX. Your PC cannot read raw TTL voltage pulses directly through standard USB ports. An onboard converter chip such as the ATmega 16UT or CH340 bridges these TTL pulses into USB data packets, allowing your operating system to recognize the Arduino as a virtual COM port. TTL stands for transistor logic pulses. These are digital signals used in electronic circuits to represent binary states on/off based on specific voltage levels. Just quickly, I want to touch on why selecting the correct board matters. So what is FQBN? That stands for Fully Qualified Board Name. It is a unique string the IDE uses to load the exact compiler settings, memory map, pin arrangement, and clock speed rules for your target hardware. Essentially, you have to select the correct board before compiling the code, which is what I didn't do here. Line by line code breakdown. So void setup executes once when the board powers up or resets. Serial.begin 9600 opens the hardware serial communication channel and sets the transmission speed to 9600 baud, BAUD. Void loop runs continuously and endlessly as long as power is supplied. Serial print LN, IoT programming is fun, transmits the string IoT programming is fun over the serial bus. The print LN, print line variant automatically appends a carriage return \R and new line \N to move the cursor down to the serial monitor, as you'll see in a second, and delay 1000 pauses the thread execution for 1000 milliseconds or 1 second before jumping back to the top of loop. Without this delay, the Arduino would flood the serial buffer thousands of times per second. For the execution steps, you need to connect your Arduino Uno to your PC using a high-quality USB-A to USB-B data cable. After you've done all the steps like launch the Arduino IDE, copy the system code, verify upload, like what we did earlier, you want to observe the physical TX and RX onboard SMD LEDs. They will blink rapidly during binary data transfers, so every time the string prints. And just as a side note as well, to open the serial monitor, you want to press Ctrl-Shift-M, and that is it for Project 1 example. Moving on to Project 2 example, the theory behind this one of why we use certain resistor levels is a bit more complicated. So I suggest that you look through the Google Docs document, which will be on the GitHub, which goes in depth. And it also explains the breadboard architecture a bit better as well. But essentially, what I'm going to do is I'll just walk through the code and the step-by-step. So for the code, the void setup part, we have pin mode 9, output. This tells the microcontroller to configure digital pin 9 as an output. By default, Arduino pins are set in high impedance input states, listening. Sending it to output prepares internal transistors on the microchip to actively deliver or cut electrical power to the circuit. So this is a very important state. We then have in the main loop block, which is void loop, the digital write 9 is high, which outputs voltage on pin 9 to high, and electricity flows from pin 9 through your LED and 220 resistor to ground, causing the LED to light up. Again, delay 1000 pauses the microcontroller execution for 1 second, and pin 9 remains at 5 volt during this entire second, keeping the LED continuously illuminated. And then we have digital write 9 low, drops output voltage on pin 9 to low, 0 volts, electrical current stops flowing, the LED turns off, and then the delay again is the same. So now the step-by-step wiring. So you want to do is power off first to disconnect the USB cable from the Arduino board to cut active voltage during assembly. Then you want to identify the LED terminals. So examining your physical LED, the longer leg represents the positive terminal anode, and the shorter leg represents the cathode, and that's the negative terminal. You want to insert the LED into 2 empty columns on the breadboard, and then you want to insert one end of your resistor into the same row as the cathode, and we're using a 220 ohm resistor. And you place the other terminal lead of the resistor into the blue common ground rail, which is at the edges. Then you want to establish earth GND. So you run a black jumper wire from an Arduino hardware GND pin to the blue common ground rail on the breadboard. Connect the colored jumper wire from digital pin 9, which we're using red in this example, on the Arduino to the terminal row containing the LED. Now moving on to project 3, it's pretty much a more advanced version of project number 2. We're going to have 3 colors, red, green, and blue. And the only real difference is that we're going to have 3 resistors as a result for each individual LED, as well as 3 individual jump cables. The only other thing to note is that we only need 1 ground cable still, and the theory itself is same for project 3 and 2. So I'm just going to jump into the step-by-step wiring now. Again, you want to start by unplugging the USB cable to isolate your circuit from active potential. You then want to position your RGB, red, green, blue LEDs across 4 adjacent vertical rows on the breadboard. And it's the exact same process as project 2. For the code, I'm just going to explain that now. So for the void setup, the pin mode 9 output, pin mode 10 output, and pin mode 11 output configures digital pins 9, 10, 11 to act as low impedance voltage drivers. This preps all 3 internal transistors to actively source 5 volts power to the respective color channels, pin 9 for blue, pin 10 for green, and pin 11 for red. In the void loop, we have the pure blue light by doing digital write 9 high, and then we do digital 10 low and digital write 11 low as well, which puts pin 11 and 10 down to 0 volts, ensuring the green and red elements remain off. And this process is then mirrored for green, with 10 being high, and for red, finally 11 being high. Once line 25 completes, the microcontroller loops back to line 7, state 1, to repeat the color sequence indefinitely. If you want to challenge yourself, since RGB LED contain 3 separate light elements in one package, you can mix primary light colors by driving multiple pins high at the same time. But maybe if you guys comment, I can do a demo on that. But that's pretty much it for today's video. I hope you enjoyed, and I'll see you in the next one.